Welcome to Rational Science. Today we're going to be talking about this lady. Her name is Sabine Hossenfelder. She goes by Sabine Hossenfelder, like they say it here in Germany. And why did I select her? Well, the other day I was discussing this gentleman, Juan Maldacena, and he's a string theorist involved primarily with mathematical visions of how this universe works. The phenomenologists like Sabine here, what they do is they want to see experiments. And so there seems to be a little bit of a schism in mathematical physics between people who try to prove or confirm the theories of mathematical physics and the other people who say, well, it's beyond hope. There's no way you're going to run an experiment to prove what happens inside a black hole, for example. And so they just want to do equations. And that's where the clash comes in, this is who Ms. I think she's married, Ms. Hossenfelder is. She's a theoretical physicist. She works at the Frankfurt Institute for Advanced Studies. That's a couple miles up here north of where I live. And she's in the superfluid dark matter group. I think she leads it. She is into what is known as phenomenological quantum gravity. And what is that? Well, it's the application of theoretical physics to experimental data by making quantitative predictions based upon known theories. So essentially what they want to do is make some quantitative predictions. But the key issue with the phenomenologists is that they want to prove or confirm their hunches in the lab, their equations, their predictions. They want to confirm those in the lab with some kind of experiment. So let's see in a little more detail what phenomenology is. This is from the Wikipedia. Phenomenological quantum gravity is the research field that deals with phenomenology of quantum gravity. The relevance of this research area derives from the fact that none of the candidate theories for quantum gravity has yielded experimentally testable predictions. And I think someone in her group, or maybe she herself, wrote that article or helped write that article. And these are the things that she's referring to: string theory, loop quantum gravity. We talked about string theory the other day. Causal dynamical triangulation, asymptotically safe gravity, and causal sets. These are the five branches that have attempted to figure out, what gravity is, specifically trying to merge the equations of quantum mechanics with those of general relativity in some way so that they get this GUT, this grand unified theory, or TOE, the theory of everything. That's their goal. Phenomenological models are designed to bridge this gap by allowing physicists to test for general properties that the hypothetical correct theory of quantum gravity has. That's their goal. That's what they're up to. Here's you can say the second part of that, and where they find some problems. Due to this current lack of experiments, it is not known for sure that gravity is indeed quantum. In other words, that general relativity can be quantized. And so evidence is required to determine whether this is the case. Phenomenological models are also necessary to assess the promise of future quantum gravity experiments. Direct experiments for quantum gravity would require around 15 orders of magnitude higher than can be achieved with current particle accelerators, as well as needing a detector the size of a large planet. As a result, experimental investigation of quantum gravity was long thought to be impossible with current levels of technology. However, in the early 21st century, new experiment designs and technologies have arisen which suggest that indirect approaches to testing quantum gravity may be feasible over the next few decades. So we're talking about something that the string theorists say, well, it's never going to happen, or if it's going to happen way in the future. Meanwhile, we're going to do the math to see if we can prove it mathematically, and that's okay. We don't need the experiment. That's more or less their idea, because they can't come up with an experiment. Some people are trying to see if there's some kind of experiment they can run for string theory, but most of them, I would say, have given up and they just do math. And then you have these other people who say, look, we're following the custom, you could say, of not only doing math, but we're going to back it up with some experiment. And that's where there's this schism going on in the church. Some people are just doing pure math, and the other people say, well, let's do an experiment to confirm string theory. And there's not much to confirm, like, what is string theory? Well, it's the vibration of a string. In the case of the graviton, which is the one that concerns us here, we're talking about a closed loop string that is vibrating, one-dimensional string. That's what they say, okay? That's what they propose. Well, how are you going to prove it? I mean, what does that change anything? We still have to show how a graviton attracts something else, what the mechanism is. And that's where these people say, let's go to the lab. So right now, these two groups are not speaking to each other. And like Sheldon Glashow, the person I named the other day, he's a Nobel Prize winner, and he's one of the first to object to string theory. He tried to keep it away from Harvard University, and they said no, he was overruled. But he said, it's not even physics anymore. And he says, who's going to work on the accelerators that we built? We have the Fermi Lab, we have SLAC, Stanford Linear Accelerator, the LHC, and so on. We have all these accelerators out there, and who's going to use them if the new generation, for the last 50 years at least, since the 1970s, have moved into string theory? And they're abandoning quantum mechanics because they believe that it's like there's nothing more to do in quantum mechanics. Or like Niels Bohr said, quantum mechanics is complete theory. Einstein said, no, it ain't. And right now, these people are thinking that Einstein was really right because it's not complete in the sense it doesn't incorporate gravitons, the gravity. Where's gravity in quantum mechanics for the small world, for the micro world? They can't include it in there. And so the string theorists have gone out there and taken the graviton and trying to merge it with black holes to see if they can figure out something along those lines, as we showed the other day. And other people like Sabine Hossenfelder, what she does is, well, she says, maybe we can discover something around the black hole here on Earth, and with the technology that we have available to us. She has hope in that sense. Okay. In fact, here's a summary of how she thinks. Okay. If I can get this in here. Give me a second. This is what she says. Wrote a paper on it. What quantum gravity needs is more experiments. Okay, you see where she's coming from with this. Math won't solve quantum gravity. Experimentation will. Okay, and she starts by saying, how she got started in physics. She says, I was awed by the power of mathematics to describe the natural world. So it's not like she's shunning mathematics. It's like she says, yeah, it's great. Mathematics is great. You need mathematics. But then she continues. She says, practitioners of these research programs were convinced they would decipher nature using nothing but the power of mathematics. And she continues, and I think in a separate paper, she says, for context, I have worked on this for many years myself, and I came to the conclusion that there are multiple mathematically consistent solutions to the problem. Only experiment will eventually tell us which one is right, is the right one. But there won't be any experiments. Okay? And part of that, she's referring in part to the string theorists, which have abandoned experiments, essentially, because they can't come up with an experiment that will show that their theory or their proposals are correct. On the other hand, she has hope, but I don't know if they can come up with an experiment that they can imagine where they can prove the existence of the graviton or how it works or whatever. Okay? So right now they're kind of like at an impasse, and the new generations, I think, are moving more into string theory because the math there has not finished, whereas the math in quantum mechanics apparently seems to be over. So they're at some kind of a crisis, I think. Yeah, that's the way I see it. Maybe I'm wrong, right? Okay, well, the problem is here. For the last 10,000 years, the rest of the world has proposed discrete particles. That's essentially what they use. What do we propose instead? We're saying that all atoms in the universe are physically interconnected. So we're proposing a totally different universe than what these people have been doing for the last 400 years. Okay, so let's see some of the differences here. Ms. Sabine is probably in favor of quantum mechanics, obviously, I think I don't have to mention that. And so what does she propose? She proposes that light is maybe a stream of particles, photons, okay? Or maybe she thinks of it as a pair of 2D transverse waves that are perpendicular to each other. They run orthogonally, okay? This is her vision of this. She's probably, very likely, I don't want to put words in her mouth, but she probably also accepts this, that this is the atom, and she will probably deny it and say, no, that's not my atom. But you say, okay, what is electricity? What is current? And she would probably say, well, it's the flow of electron beads from atom to atom. You know, they go from valence band to valence band. And so we have to go back to the atom and ask her, okay, what atom did you use to do electricity, to do current? And she's had no other choice but to go with the planetary atom that Mr. Bohr and Rutherford came up with. In other words, with the orbiting bead. And they can put that bead anywhere they want. It doesn't matter. The point is, why doesn't that bead fly away spontaneously? Why is it stuck to the nucleus? What is the yellow stuff that keeps it bound to the nucleus? That's what they have to answer. And if they can't answer that question, they can't say that electricity is the flow of electron beads. And I don't care about Mother Nature's atom here. I care about their atom. What is their atom, the one they're going to do their electricity with? They can't bring that atom, the planetary model, say, okay, this is electricity, and then you say, is that your atom? Oh, no, that's not my atom. This is the way they handle these things. This is where the problem is. Okay, what do we propose instead? Well, we propose something new, and that is that all atoms are physically interconnected. They're interconnected by what you see on the upper right there. Light is a torsion along a rope. All atoms are connected by a rope-like, DNA-like mediator. And the mechanism is that as the atoms expand and contract, they torque the rope. Light is torsion along a physical rope. Torsion is the fastest thing imaginable. It explains why light is so fast. Okay, and at the bottom right, you'll see the construction of the atom. The rope is made of two threads. One of the threads goes through the center of the atom, builds the proton star. And all the atoms in the universe contribute one thread to the proton star. All the other atoms in the universe, they contribute another thread, and that one coils around and forms the electron shell, a membrane that encapsulates the star. And there you see the model. We're saying that when the atoms expand and contract, they torque the rope that is made of the same things that the atoms are made. The underlying hypothesis is that there's a single thread in all universe. That's it. And what this thread is it builds atoms and ropes connected to atoms, connected to ropes, connected to atoms, connected to ropes, all the way down the line. So it's a single thread in the entire universe. Very different than the particle world, the discrete particle world that quantum mechanics and general relativity propose, and on which string theory bases its equations as well. Okay, one of the things you can explain with this is the speed of light, and here you see it. You see the wave equation of light. Light travels always at the same speed between any two atoms, irrespective of whether the atom forms part of a dense medium or a lighter medium. It doesn't matter. Between any two atoms, the rope always travels at the same speed. Why? Because if you see there, in fact, I can probably mimic it better with my rope here. Okay, you see what a couple. If my fist, let me remove this for a second here. If you see there between my fists serve as atoms, and what do you see? 3 links maybe. Okay, so we torque it some more. Okay, we torque it some more, and now you're going to see more links, and each link is shorter. Okay, so the links have become shorter, meaning the link length or wavelength, if you want to call it, has become shorter, and there are more links. There's more frequency. Okay, so this equation, the one I showed here, that's the equation of a rope. C equals frequency times wavelength. That is the equation of a rope. And there I show it in pictures. If you torque the same amount of rope, you torque it more and more and more, your links are going to be shorter, and you're going to have more links. Frequency, wavelength. We're done. Okay. And there in the prism on the bottom, you'll see that if you have white light coming from one area of the and hitting the prism, on the other side, you don't have waves coming out or particles coming out as in mathematical physics. That's a Ptolemaic explanation for light. Now, what you have is the difference in link lengths for the red color, which is longer, and for the bluish side of the spectrum, which the links are shorter and the frequency is higher. In other words, there are more links. We're done. That's how simple it is. This takes us to the checklist of light, something quantum mechanics cannot pass. Light is fast because it consists of a torsion propagating along a helical DNA-like medium. How can quantum mechanics justify the speed of light? Why is it so fast? I mean, and why isn't it faster? Like, why don't those photon particles, why don't they travel faster? Why does the wave travel faster? Why are they one-way mechanisms? See, a rope is a two-way mechanism. That's the difference also there. But aside from that, torsion is the fastest thing you can imagine. So we're talking about a 3D wave here, okay? Speed of light, c equals frequency times wavelength. We can see why wavelength and frequency are inversely proportional. A photon is massless because it is the mediator. It's the thing that interconnects what we call mass, the atoms. Okay? The electric field runs perpendicular to the magnetic field, and a taut rope invariably embraces an imaginary axis, as you can see in the GIF below. You can see that there's an imaginary axis. Now you can see why light is so straight, or why the goosebumps there travel rectilinearly along always in a straight line. Why would a transverse wave not deviate if it's one way? Why don't a series of discrete particles, photons, travel straight? Why would they travel straight? That's what you got to explain. There's no reason. Why don't they just go in different directions? And light has an undulatory nature not because of traveling transverse waves, but because a rope spinning around its axis exhibits goosebumps moving along its structurally wavy surface. In other words, a rope is wavy by nature. It's its structure. And of course, all ropes have amplitude. Okay, it's an attribute of a two-strand rope. Okay, one of the problems that quantum has, it cannot answer, is entanglement. Okay, and here you see it. If you have two particles which are light years apart, 100 billion miles, kilometers, whatever, okay? One goes clockwise, the other one goes instantaneously counterclockwise. They have no idea how that happens, and it's been so-called confirmed through an experiment. Alain Aspect did it in France, I think in the 60s, and he showed that it's a feature of the quantum world. But what did he show? He didn't show that it's mediated by particles. What he showed is that, yeah, effectively, if you check light here, the light at the other end, or electron, if you're doing it with electrons, the other one over there it goes in the opposite direction. And how do you do that without a mediator? Are you going to put angels in there, spirits, like quantum mechanics does? Is that how we're going to do it? Under the rope model, it's baby stuff. It's kindergarten stuff, EPR, or entanglement. Any rope, if you look at it from one end, it could twirl clockwise. Your friend at the other end should see it counterclockwise. And when you reverse the spin of your angle, like you go from clockwise to counterclockwise, well, he should see it clockwise on the other end, okay? And here, let me show you what I mean. See if I can do this, okay? There. So I'm going to turn mine clockwise. Hopefully your end turns counterclockwise, okay? You see that? Now let me turn my end counterclockwise, okay? Hopefully your end is moving clockwise, okay? So, a rope can explain it without any problem. That's what they've been looking at all these years. The rope models all features that we've seen or that we've verified about light. Here's another headache for quantum mechanics. It's known as the Slit Experiment. Okay, we send these photons or these electrons, depending on how you do the experiment, and we see these fringes on the wall when that goes through a pair of slits. But we're going to do something else. We're going to replace the slit with a needle, which is the way Thomas Young did his second experiment. Now the electron beads or the photon beads have nothing to bounce against to interfere at the screen. Okay. On the other hand, with a rope model, which is what you see on the right, very simple. All atoms are interconnected before you turn on the light. Everything's already connected, atom to atom, by two-strand ropes, twined two-strand ropes, right? They're coiled around each other. And what happens? When you turn on the light, all you're doing is increasing the number of links, and each link is shorter. Now it comes within visible range, okay, the light. And what you see is then standard interference, both constructive and destructive interference, according to what we've always done with waves. Nothing's changed. The only change here is that now we know that there is a physical entity in that space. It's the electromagnetic rope. And once we have this mediator, we can explain very easily why there are all these interference fringes. We have a physical interpretation for something that has driven quantum mechanics just nuts, okay? Okay, how about electricity? We were talking a minute ago about electricity. Here's the version from quantum mechanics against the rope model. Okay, according to quantum mechanics, what you have is the bead going from atom to atom. That's what they say. But for that, you have to tell me what your atom looks like. Otherwise, you can't say that that's what Mother Nature does there in that secret world of hers. On the other hand, under the rope model, very simple, we have all the membranes, which are the electron shells, okay, just like in chemistry, same thing. But they're merged, they're blended into each other, and they form molecules. It's the blending of membranes. And again, I've talked about that in the past. I'm not going to go over the details here, but they blend. And once they blend, they form these long, what we call serpentines. The serpentine spins around an axis, okay? And that's electricity. And electricity is not negative and positive. Mother Nature doesn't understand what negative and positive and numbers are. She understands physical objects. And here we have a physical object, a serpentine we call it. And in one end it's clockwise, the other end is counterclockwise. That's it. And you can do an alternate current. You can switch it back and forth between clockwise and counterclockwise, going in one direction or in the other direction. Very simple. Okay, what does that lead to? Well, we have here a typical circuit, the basic circuit that you learn in electricity, okay? And what do we see? Well, we see that when we close the switch and have a closed circuit, in the case of quantum mechanics, what you have is all these electron beads flowing from atom to atom. In the case of the rope model, what we have is something else. What we have is a snake that is coiled around and its tail is touching its head. That's what it is. And when the snake twirls, it twirls on itself. And what you're seeing is this twirling there. I try to mimic that as best as possible. The way we do it, we start with the iron atom. I'm blending all these iron atoms in a wire. We're going to assume the wire is made completely of iron atoms for simplicity's sake. Okay, so there's your atom. Okay, and now we're going to merge it with those shells. Those electron shells are merged one with the other, and they form these long chains. Okay, and now when we close the circuit, these are going to spin. And when they spin, that's what we call electricity. Electricity is a clockwise, counterclockwise motion of this wire, of this snake that is touching it. It's coiled around from head to toe. And the signal moves in both directions simultaneously. Remember, it doesn't matter if you go from tail to head or from head to tail. It just spins in place, okay? So very simple, very different than what quantum mechanics proposes, and classical mechanics really for that matter. So we're replacing the electricity that all these people had for now 200 years. We're replacing it with the rope model. Okay, how about gravity, which is what the key issue is. Here we have gravity, and we have the string theorists. They say that this is a graviton. It's just a closed loop thread, and it's a vibrating thread, and this one-dimensional thread somehow converts into a three-dimensional ball, which is supposed to be this graviton. Okay, well, of course, people in quantum mechanics are not very fond of that notion. But what do the people from quantum mechanics propose? And here you see it. They work with what are known as Feynman diagrams. Okay, and you have here two electrons. They're moving more or less parallel, and they shoot a photon at each other. And you can explain with this how they push each other away, even if you're going in time reversal, from the future to the present, which is another nonsense that they have in mathematical physics. Now here, we can explain anyways with this model why an electron can push another one away by throwing a photon at it. Okay, fine, great. How do you explain this with gravitons? I mean, gravitons has to explain the opposite thing. It has to explain with this same model how one electron or one proton or one atom or whatever, or a rock attracts another rock. So if I have two rocks, why would, with certain mass, right? Why would a rock attract another rock? Does it throw gravitons at it? If it throws a graviton at it, it's going to push it away, not pull it inwards. What you have to explain is the mechanism. How do you pull with discrete particles such as gravitons? That's where the problem is. And what quantum mechanics has not been able to explain and will never be able to explain is attraction, pull, the force of pull. They can explain push very easily, but they're missing half of the forces in the universe. They can't explain how gluons pull, and they put this bed spring holding the quarks together. That's cheating, because when you go to the standard model, you don't find bed springs. What you find is a little ball, and they call it the gluon ball. Okay, and you find only balls in there. So we don't have a gluon. Can I explain how it attracts, physically attracts two quarks together? The graviton ball particle, right, cannot explain, even if you don't consider the classical one. Let's take the quantum one, which is a magical particle, right? But even with a magical particle, you cannot explain the force of pull, because the only way you can do that is through a Casimir effect type mechanism where you remove whatever's between them and the forces from the outside push it in. You have to use push, pressure. You can't do pull in a sandbox. And that's what quantum mechanics is, a sandbox. They don't see it that way. They see it as a beehive, like all the bees buzzing around. But what they're explaining, or what they're describing, really is a sandbox. And no, you can't imitate Mother Nature's universe with a sandbox, with a quantum sandbox. Okay. So what's the model that we propose? Here it is, very simple. All atoms in the universe are interconnected, so action at a distance is not a problem. It's just that there is no action at a distance. We simply cannot see or touch the mediator. That's what it is. So when I have a little pencil and I let go of it, it falls to the floor. Why does it fall to the ceiling? And you say, well, I don't see anything here. I can't touch or see anything between the pencil and the floor. Why did it go to the floor? Why does it go to the center of the earth? Why does it always converge upon the center of the earth? Well, because hopefully in science or in physics, we do everything with objects. We don't do them with spirits or angels or energy or mass. No, we do it with physical objects. Mother Nature works with physical objects. We have to explain why the earth doesn't fly out of the solar system. What are you going to say? That there are angels that mediate the attraction between the earth and the sun while the earth is moving around the sun in this angular momentum trajectory? So no, there is no magic. Every atom is interconnected. So if you see the cube and the cylinder there, you have 5 atoms in the cube attached to 1 atom in the cylinder. They're all on the same axis. Okay, but as the cylinder approaches, they all go outside the axis and act independently. And the closer you are, according to Newton's equation, right, distance squared on the bottom, mass distance squared, the closer you are, the stronger the force. And there you see it. You see why? Because at different locations, the ropes fan out, and you have a different weight between, in other words, the weight of the cylinder with respect to the cube. So if you're very far apart, like shown in the bottom set of 3 pictures there, you're very far apart, all the ropes converge and act as one, like a single coaxial. And as the cylinder approaches the cube in space, right, the ropes begin to fan out, and now the acceleration is greater and greater and greater until they're very close by, and all the ropes essentially are completely at different angles. Almost none of them are on the same axis. Very simple mechanism. There you have the acceleration of gravity. Here I've made a couple GIFs that show this as a picture. Here's an astronaut falling to Earth, and you can see what's happening to the ropes. They fan out. Every atom in his body, which I didn't draw all of them, every atom in his body is connected to every atom that comprises the Earth. Now we can see why there is an acceleration of gravity. And likewise here we can see why the Earth doesn't run out of the solar system, because every atom of the Earth is connected to every atom that comprises the sun. And since space is absolutely nothing under the rope model, in other words, we have to define these terms and say that space is that which has no shape. That's what vacuum is. That's what nothing is. That which has no shape, and so no form. Okay, so there's nothing for the Earth to rub its elbow against. Space has no friction with respect to the Earth, and vice versa. And so the Earth is twirled around by the sun forever, unless there are other factors like other planets that are pulling on it and so on. But other than that, if these were the only 2 objects in the universe, the Earth would travel forever around the sun. Okay. So there you have the mechanisms, okay, and you can see the differences between what mathematical physics proposes and what the rope model proposes. Okay, let's get one more item, because this is what Ms. Hossenfelder works on. She works on dark matter. She's been led to believe that there is something called dark matter out there. What is dark matter? Well, dark matter is a variable that was included in an equation so that the equation matches observation. What did they observe? Well, they observed something like this. They observe a galaxy twirling around, and they say, look, the stars on the outside of the galaxy, first of all, they don't fly out. You say, why don't they fly out? I mean, this thing is twirling. These, like when you're in a carousel and you're hanging on, and if it goes faster and faster and faster, hey, you're going to fly out of there unless you hold on to something, okay? If you're just standing there and this thing starts rolling faster and faster, you're going to fly out of there. Well, why don't the stars do that at the edge of a galaxy, especially at the edge of the galaxy? And then the other thing is the stars at the edge of the galaxy, you would think they travel slower, like Pluto travels much slower than Mercury. Mercury does its route in 88 days, Earth days, and Pluto takes 248 years. So Pluto is quite slower than Mercury, right? That's not the case with stars. Stars on the periphery, on the edge of a galaxy, travel faster or about as fast or faster than the ones on the inside. How do you explain that? And so what they did was sprinkle kilograms. They sprinkled kilograms here and there, and they say, oh, we fixed it. Now we know why these things don't fly out, because there's these dark kilograms, and they call them dark matter. And this is what this lady studies. She studies this inexistent spirit called dark matter. And they convinced her that there's dark matter. Why? Because there's no other explanation in their minds for how this could work if you do not do it with gravity and mass, in other words. You have to sprinkle mass in there to get the equation to match observation. That's essentially what they're doing, okay? And now she's going out there trying to prove the existence of dark matter, or that's already been proven in their minds. What they're trying to do is go to the lab and say, let's confirm that proof, that evidence. Let's get the evidence, right? And again, evidence, we don't use that in science. Evidence is what you use to persuade people. And she never learned that either. She thinks that science is about getting proof, running experiments, and creating evidence so that you can convince someone, including yourself, right? You want to certify that what you believe is true, and so you say, I'm going to run an experiment to see if my belief is true. Okay, so how do we do it in real science, in real physics? Well, here you have a galaxy, and what we're going to assume that all atoms are interconnected. That means that all stars are also interconnected, physically interconnected. So we lay our web, our spider's web, on top of the stars, and so that you can understand what's happening here. We're putting that web. We're assuming this is a web. Most of it is, you can't see it, okay, or touch it if you could be there, right? And it's because the whole galaxy rotates as a single carousel, a single disk, okay? And that's why the stars don't fly out first. And second, that's why they fly or travel just as fast as the ones on the inside, or faster. There are different reasons for that. I've explained that in the past, but I'm not going to get into that now. The issue is that if all stars are interconnected, we can explain why the stars on the outside travel just as fast, at least, as the ones on the inside, okay? And because they're all connected. They're all physically connected to each other. So the whole thing rotates as a single disk, as a single carousel, okay? And yeah, I didn't show it there, but we have to include on that the magnetic field of the galaxy, which is another can of worms, but I'm not going to get into that today. Anyways, you can see the differences between what quantum mechanics, especially Ms. Hossenfelder, proposes, because that's what she's been educated on, that's what she memorized in school, and that's how she got her degree. Okay. Now it turns out that, they ask, well, why can't you see or touch this rope that you talk about, Bill? What are you talking about? I don't see any ropes. When you let go of the pen, do you see anything here? And you might say, well, there's air here. I don't see it, but there's air. Okay, fine. But we can do this in outer space. In fact, the astronauts took a hammer and a feather to the moon, for those who are not flat earthers. Okay, they took them to the moon and they let go, and then there's no air there, and both of them fell at the same time, more or less, right? So yeah, there's nothing here. And so where are these ropes that you're talking about? I mean, you're saying these ropes are physical, yeah, and I don't see them, I don't touch them. What's the problem? Okay, so let's find out what the problem is with all these people and why they never discovered that, and they never would have, because this is where the problem is. This is the what they operate under. They operate under the wrong definition of the word object. In fact, it's even worse than that. They never defined the word object for the purposes of physics. In fact, they never saw that it was so important to define the word object in order to explain and give a physical interpretation in physics. If you look at a pulley, you pull on a rope, it goes around a pulley and pulls a box up. All the objects there you can see, touch, you recognize each one of them. You recognize the box, you recognize the pulley, you recognize the rope that's pulling through, it's wound around the pulley that's pulling on the box. And so it's all done with objects. There's no angels there, and there's no energy, no mass. When you say someone, how did you pull the box up? Well, I pulled it with a rope that was wound around a pulley and just pulled the box up. Or like I showed in the other video last time, you have Felix the cat, and he throws a horseshoe through a window, and it breaks the window. So I go and show this to an audience and say, how did Felix break the window? How did the window break? Everybody would say the same thing. What I saw is that a horseshoe went through the window. Straightforward. That's objective. Because everybody sees the same thing. Everybody will tell you the same thing. That's how the window broke. That's known as physics. That's known as objective physics. No proof, no evidence, no experiment. We don't need any of that. We just need an objective explanation, physical interpretation for how the window broke. And everybody saw the same thing. And but the problem here is that these people are relying on the wrong definition, or an irrational definition of the word object, of what a thing is for the purposes of physics. All these people think that it's a question of visible and tangible, of see and touch. And it never dawned on them that this is not a question of using the senses. Because first, you need two objects to do see, and you need two objects to do touch, as you can see there. The asteroid has to touch the Earth, okay, for there to be touch. Okay, you need two objects, so you can't use the definition see, touch, visible, and tangible as a criterion or criteria, if you're using both, to define the word object. That's where the problem starts. Okay, these people never define the word object. It's the first word you got to define in the discipline known as physics, because you can't do physics without an object. And they never learned this. This is the golden principle, the non-negotiable principle of physics. You can't do physics without an object. You need an object. You can't do physics with concepts such as energy or mass or charge or field. You can't say you transferred energy. There's no such monster in physics as energy. Or like Mr. Feynman said, we don't know what energy is. Of course not, Mr. Feynman, because energy is not a what. Energy is a spirit. Okay? It's a spirit that mathematicians have used as a physical object for now over 100 years, no, even more than 100 years, since the days of Aristotle. Okay, so what is an object? That's what we need to define first in physics, and here we have to define, and here it is. Okay, object is that which has shape, and first you have to define the golden principle of physics. Physics requires an object. You can't do physics without an object. Can you see the air? No, you cannot see the air. Does that mean that air is not a physical object? Yes, air is a physical object for the purposes of physics. Air is not an object in ordinary speech, and people, have their ears torn when I say that. But yeah, air is a physical object. It's made out of atoms, and hopefully an atom is a physical object. So anything that is made out of atoms hopefully is also a physical object. The fact that you have all these loose particles running around, it doesn't mean it's not a physical object. Does air have shape? Yes, of course, air does have shape. And that's another thing that people get very confused about, because they say, what's the shape of air? Wrong question. Wrong question. The question is, what is the shape of energy? What is the shape of a tree? What is the shape of a house? No, the question is, does it have shape? So you take air in a balloon, and the astronaut takes it out there into space, and he pops the balloon in the middle of space, in the middle of nowhere. And it turns out you color-coded the air just so you could see it, right? And it turns out you see a blob come out. Once you pop the balloon, you see a blob come out. And it's an irregular blob. You say, what is the shape of that blob? Wrong question. Does that blob have shape? Does it have form? The answer is yes. We're done. It's a yes or no type of question, not a what. What is the shape of? No, it's does it have shape? And shape of air here on Earth is very simple. It forms a shell around the Earth. So it has the shell shape. So yes, air does have shape. Air is a physical object for the purposes of physics. And you can definitely say that it was air that was in motion that blew my house away. Some call it a tornado or a hurricane, whatever. It doesn't matter. It's air, moving air. The object was air. That's what we call that bundle of atoms. Okay? Does it have shape? Of course it does. It has a surface. That's why it blew your house away. Okay, with that, we'll see you next time. And bye-bye. I'll see you on Sunday. Bye-bye.